So now let's consider the case where the channel can corrupt packets. Okay, and let's see if this protocol 2 works. So probability of corruption is non-zero. Okay, remember this protocol 2 was designed so that the data packets can get corrupted, but in the beginning let's assume that the ACK or NAC don't get corrupted. Okay, so what happens is the sender sends some data and it waits for a ACK or a NAC. If it gets a NAC, it resends the packet. If it gets a ACK, then that's done and that's it. It's a very simple protocol. So let's try to implement this. So remember, notice that there is an exercise which is provided along with the lab. So this is the exercise. These are some instructions. So the first problem is to just go through the existing code, okay, and run it. And now let's set probability of corruption to some number which is non-zero and check that the first protocol fails. So let us actually do that. Okay. So let's open this test bench file. So we are using the first protocol, protocol 1, and probability of corruption was already at 0. So now let's corrupt the data packets. Let's set this to 0.5. So half of the data packets are corrupted. And now let's run the simulation. We expect that this protocol should not work because some packets get corrupted. When they get corrupted, such packets are discarded. And then the receiver will complain that some packets were missing. So let's see if that happens. Okay, so we have 3. Okay, so indeed we can see this error. So the sending app sent packet 0. Okay, and where is the receiving app? So what happened is the first packet that was sent was corrupted. Packet 0 was corrupted and it was not delivered. Then after 2 units of time, the receiver received a corrupted packet and it discarded it, didn't do anything. At time 8, the sending packet sent the next data 1. Was it corrupted? Sender sent it. It was sent on the channel. Receiving app received data 1. So after some time, so it was sent at time 8. So 8 plus 2. So after 2 units of time at time 10, receiver received that packet 1. Okay. So receiving app received data 1, but it was expecting data 0. So it directly didn't get packet 0, it just got data 1. And so this error printed. So basically, essentially what the RDT receiver is doing is just discarding corrupted packets and only delivering those packets which were not corrupted. So in sense, this protocol is not doing anything. It's not providing any reliable data transfer. So this fails. Okay. So this is a symptom that we observe. So now let's try to implement this simple protocol where data packets can get corrupted. Okay. So let's first go to this test bench file and let's set this corruption probability to 0.5. So data packets can get corrupted. And now let's use protocol 2 instead of protocol 1. Everything else remains the same. We don't have to change anything else. So where is protocol 2 implemented? So this protocol 2 is provided in the template. So protocol RDT2 is actually provided for you. So let's see what it does. So this is a simple NAC or ACK based protocol, right? So sender side sends the message and keeps waiting for a ACK or a NAC. So it should have 2 states. So let's do this. The sender, so recall this protocol, this is the sender. It has 2 states. Okay, first state is that it's waiting for a call from above, and the second state is it is waiting for a ACK or NAC. So let's see. So I declare 2 variables, waiting for a call from above, which is state 0, and waiting for a ACK or NAC as state 1. And the sender is initially in state waiting for a call from above in the beginning, in the init. Okay. So let's see now what does it do. So this is the behavior. So when RDT send is called, if the sender is in this state, it is waiting for a call from above, then it could accept this message and send it as a packet. So what does it do? It creates a packet, sends it, and then it goes into the next state, which is waiting for ACK or NACK. Fine. Let's look at the protocol again. So this is what happens. What happens if it is in this state, waiting for ACK or NACK? One of two things could happen. One is this and one is this. So the first thing is that it gets a packet and it is a NACK, in which case it has to resend the packet and go back to the same state. Or it could get a ACK, in which case it has to do nothing and go to the state back. So let's implement this in code. Okay, so in the receive, if RDT receive is called, so there is an assertion here. What does assertion do? So I know that RDT receive should only be called when it is in the state wait for ACK or NACK. It should not be possible that you are in this other state where you are waiting for the call from above, but you receive a packet. You receive an ACK or NACK. That should not happen, correct? So I am just putting it here so that that belief gets tested by an assertion. So there is an assert statement in Python wherein you put some condition. If ever during the simulation this condition is false, the simulation will stop, Python execution will stop, and this assertion error will be printed. So it is just a way of checking that this situation never occurs. So whenever I am sure that some situation should never occur, I can add an assertion statement. So now let's see what happens on the receive. So on RDT receive, when RDT receive is called, either it could be a NACK or it could be a ACK, and accordingly I have to take the action. So let's implement this. So if the packet payload is a ACK, then everything is fine. Then you change the state to waiting for a call from above. If the packet payload is a NACK, then I need to resend the packet. So I call channel.udt send and again packet to be sent. So where is the packet to be sent? It was already initialized here, right? Packet to be sent was initialized here, so I sent it again. That's all right. Okay. Else if you receive any other payload, then prints error. Okay. When can it receive something which is not a ACK or NACK? When it receives a corrupted packet. Now this could not happen if the ACK channel is perfect, but it could happen if the ACK channel also corrupts packets. So we have just put this here just in case. Okay. So what is the receiver's behavior now? The receiver's behavior is this. Okay. It has just one state and it's waiting for a packet. And one of two things could happen. The packet could be corrupted or it could be not corrupted. So if the packet is corrupted, we have to send an ACK. If the packet is not corrupted, then we can extract the data, deliver it and so on and send a ACK. So that's a very simple thing. So let's see what the receiver should do. There's only one function, RDT receive. It receives a packet. If the packet was corrupted, then we send an ACK. Okay, send it across the channel. Else, if the packet was not corrupted, then we send a ACK. Extract the data and deliver the data. Fair enough? So this is the simple protocol 2. Let's see if this works now. So earlier we had this error where the receiving app received data 1. So data packet 0 got corrupted and it was never resent. So now let's run the simulation again and see if it works. So let's just make sure that this is indeed there in the test bench. So this is a testbench.py file. So we have set probability of corruption equal to 0.5 for the data channel. Half of the packets get corrupted. And we have selected protocol RDT2. So it should work now. So RDT2 is already a file in the same folder. So let's run this simulation. So what do we observe? There is no error printed. It does run for time almost 100. Okay, it runs for 100 units of time. So basically after 98 no event happened, that's why it's not printing, but it ran for 100 units of time. Let's see if ACK or NACK were being sent indeed. So at time 1 it sent data 0 and the channel did not corrupt it, the receiving application received data 0, that's fine. At time 5 data 1 was sent, okay. Now what happens here? This is interesting. So sending application send data 1. Now RDT sender, where is RDT sender being called? So notice something interesting is happening here. So the sending app sent data 0, it went on the channel, okay, and an ACK was sent for it, and the receiving application received data 0. So that's fine, that happened. Next, the sending application sends data 1. And then there is this same thing printed again at time 8. So what is happening here? Okay, so something interesting is happening here. Why is this sending data 1 being called twice? So let's look at this state machine again of the sender. So initially the sender sent data 0 and now it is waiting for a ACK or NACK. While it is waiting in the state, what should happen if RDT send is called? It's actually waiting for a response. In the state, what if the application says RDT send? It should ignore it, right? It should say hold on. It should not accept that. So that's what is actually happening. So let's look at the code for the sender again. Okay. So let's look at the sending application. If it's in the state waiting for a ACK or NACK, okay, and if RDT send is called, so if its state is not this but it is actually ACK or NACK, then what does it do? It returns false. So it just says to the application that I'm not ready to receive this message. And let's look at the file application.py. So when sending application tries to send something, okay, it tries to send it, so it says RDT sender tries to send it, it gets a false, so it's not a success. Okay, so this if condition is false. So what does it do? It just tries again after some time. So it's better to say trying to send data. Okay, trying to send data. This is a more accurate representation. And if it is success, then it should say successfully sent data, right? So it just makes an attempt to send the data, but if the RDT sender is not in a state where it can actually receive this, it just tries after some time again. So this condition is false, so again this is implemented, and after some amount of time it tries again. So that is the correct behavior that we want to implement, and that is what is happening here. So let's run this again and see. So we have the sending application trying to send data 0, it gets sent, and the receiving application receives it. Now at time 4 it's trying to send data 1, but it's not able to, so it retries after some time. So at time 9 again it says trying to send data 1, and now this time it's successful. So what has happened? Okay, at time 3 the ACK channel starts sending the ACK packet, and after 2 units of time, that is so 3 plus 2, that's at time 5, the RDT sender receives this ACK, correct? So this goes back into the waiting for above state, the sender. So at time 9 it's able to actually send the next packet. Okay, so are we missing a print statement? Yes. Okay, so when the RDT sender gets a ACK, it should print something. Okay, so RDT sender and RDT receiver don't have any print statements in this example, so it's your job to add some print statements to make sure that this works. Okay, so please do instrument this code protocol RDT2 with lots of print statements to show the status. Okay, just like we added some print statements in protocol 1. So now this is what it does. So let's now go to the RDT receiver. This is the simple code. Okay, so we have the RDT sender, RDT receiver. Okay, so what does the receiver do? It checks if the packet is corrupted, it sends an ACK, else it sends an ACK. So you need to add print statements in each of these cases so that you are able to observe the output. Okay, so now let's go back to the exercise. So the exercise asks you to look at protocol 2 and check that it works if you set the probability of corruption to be non-zero for the data channel. But this protocol will fail if the probability of corruption is non-zero for the ACK channel as well. Okay. Now here is an interesting question. It says, as you increase the probability of corruption, how does the average time to send 1000 messages vary, and so on. So there are lots of interesting exercises henceforth, and incrementally this exercise will lead you to implement protocol 3. Okay, so this requires implementation of timeouts. So how to implement timeouts is given in this skeleton. So I hope that this is an interesting assignment, and I hope that the guide was sufficient for you to get started with this assignment. So thanks, bye.